quiz. Okay, so let's move on to now deriving the Kepler's laws. I will start with the second law, the area law, and I will show you a proof that is actually Newton's proof. So this is roughly how Newton proved Kepler's second law. So imagine you have the Earth in space, and from some external point we are looking at Earth and we connect Earth to this external point. And imagine that we made the sun disappear. So we got rid of the sun, we got rid of all of the planets. It's only the planet Earth sort of sitting in space. Well, in fact, not necessarily just sitting, but the point is that the law of inertia tells us that if there's nothing acting on Earth, it should move in a straight line at a constant speed, which means that if we wait something like a month, let's say, our planet will move along a straight line, and this line segment connected to an external point will sweep out a nice triangle, right? So there is no sun, nothing acting on the planet, it's moving along a straight line with this segment sweeping out a nice triangle. Let's say we wait another month, so another month goes by and we have another triangle. And my claim is that these two triangles will have the same area. The reason they have the same area is that this side along which the planet traveled, these two sides are equal. So because it was equal times and it was the planet was traveling at a constant speed, right? So it traveled some distance in the first month and then traveled the same distance in the second month. So these two triangles have the same side, have these sides being the same length, but the triangles are also of the same height, because if you look at the line of these sides, containing these sides, it's from a certain fixed distance away from this external point. Okay, so and that is the height. So this is a perpendicular line showing us that these two triangles have the same height. So they have the same base and the same height, meaning that the area, which is 1/2 times the base times the height, is the same for both triangles. Okay? So this was the case where we didn't have the sun, we didn't have anything else in place. Now let's assume that after 1 month we put the sun back into that point, external point that we have looked at previously, and we put it back in, turn the sun on just for a moment, okay, after a month. And that turning the sun on just for a moment gives the planet a tug, like a pull on the planet, which will result in sort of a motion of this planet being added to the previous one. So instead of going along the original red line, it's going to deviate, and in a sense that in a way that we are going to have a new orbit. But imagine that remember that we just put the sun back in for a moment. So after we switch off the sun, the planet still should still move in a straight line, in a way that this tug that the sun gave the planet should combine with the original motion, putting it up there, the planet. So what we got now is a third triangle, in fact, and my claim is that this third triangle has the same area as the second one. So it's easy to see that they share a common side. So we have this green arrow, this on the bottom. So that side along the green arrow is of the same length, is the same side for both triangles, and they have the same height as well because they are between parallel lines. So the two green arrows give you two parallel lines, and these two triangles, the third triangle and the second one, are between these parallel lines, so they must have the same height. So again, the second and third triangle share a base, and they have the same height, so they have the same area. So what we have seen is that the first triangle had the same area as the second triangle, and the second triangle has the same area as the third triangle, so we can get rid of the second triangle, and this area law remains valid not only when we don't have the sun and the planets and anything, but even when we put the sun back in just for a moment, okay, after 1 month. So you can imagine keep doing this. So instead of these blue segments, so instead of going straight, the planet gets a small tug after each month when we just put the sun back in its place for a moment, and it forces the planet to go along this broken line, this red segment. But the point is that by the previous argument, each time this line segment connecting the planet to the sun sweeps out the same area, sweeps out triangles that have the same area, okay, each time. So this is after 4 months, but of course, so we get this orbit, and the area law, Kepler's second law, is valid at this point. But no one told us to choose to put the sun back in every month. We could do that every 2 weeks or every week, or if you look, but even if you don't look, the sun is there pulling on Earth constantly all the time. So if you would repeat this and further divide the time intervals, you would get a nice smooth orbit in a way that this line segment connecting the planet to the sun would sweep out equal areas in equal times. So this is the end of the proof. This is Newton's proof of Kepler's second law, the area law. I hope you liked it. When I first saw it, I thought it was really nice, using some elementary geometry to prove something about planets. Is I think it's fantastic to be able to do that. I mean, all we use is triangles, and we proved something about planets. Okay, so next I want to show you a bit more, well, the same thing, but a bit more rigorous maybe. So now we have the vector r, which connects our planet to the sun, sweeping out a triangle, right? So what we have here is the planet has this vector going to it from the center at time t, and then some delta t time later we have it in another position, but it sweeps out a nice triangle. And my point is that the area of this triangle can be calculated using the vector product. So now I'm starting using the vector product and scalar product. So if you remember what this vector product is it's a vector that you get from two given vectors, so that this new vector is going to be perpendicular to the previous two, and it will have a length that is that has the area of the parallelogram spanned by the two vectors that you start from. Okay, so the length of the vector product is equal to the area of a parallelogram spanned by the two vectors. So if you want to get the area of the triangle, you want to divide by 2. So that's what that is what is happening here. So we have these two vectors, RT and RT plus delta t, spanning a triangle, but if you would complete it to a parallelogram, you would get the length of the vector product. So I'm multiplying it by 1/2 to get the area of the triangle. Okay, so the rate of change in area is now given by this vector divided by the time that has passed, so the time interval. So if you divide this vector by delta t, what you see here appearing is delta r over delta t. And if you take delta t to 0, if you consider shorter and shorter time intervals, this displacement over time is going to tend to the velocity vector, okay? So the rate of change in area is given by the magnitude of this vector, which is 1/2 times the position vector cross product, cross multiplied with the velocity vector, okay? And in fact, we've seen that this is something that's constant, and this cross product of the position vector and velocity vector is very similar to something called the angular momentum. So if you have heard in physics, we have this physical quantity called the angular momentum, which is this vector capital L that is given by the position vector, the cross product of the position vector and the mass times the velocity vector, okay? And what we have seen here is that it's a conserved vector. It's a fixed vector that remains the same as time passes. And in fact, what we have seen in the previous proof as well, Newton's proof, and what you can see here as well, is that the motion has to take place in a plane that is perpendicular to this fixed angular momentum vector. So we have this angular momentum, and since we obtain it from the position vector and the velocity vector and take their cross product, so L has to be perpendicular to the position vector and the velocity vector, and it's a fixed vector, meaning that R, the position vector, will be staying in that plane perpendicular to L. Okay, so it's a conserved quantity. The motion takes place in the plane perpendicular to L, and the area swept out in equal, in 1 unit of time is of course the length of this vector. But if you look at this vector, you get this from L by dividing L. Dividing L by 2m will give you the rate of change in area. So the length of L divided by 2m is going to give you the area swept out in unit time intervals. Okay, so this is Kepler's second law, and in fact, if you looked carefully in Newton's proof, we didn't use anywhere the fact that the sun has the gravitational attraction that is inversely proportional to the square of the distance. So nothing was assumed about the strength of the gravitational pull. The only thing we assumed that the gravitational pull has a center, so it originates from one point. Okay, so in fact what you could prove, and here is a derivation, is that for any central force, any force that sort of originates from one point, this angular momentum is conserved, and Kepler's second law will hold for any central law, any central force law, not just the inverse square law. And let me just quickly show you how this can be proven. Well, there is that bottom line, but let me show you using my notepad. So here I have, just to show you this Leibniz rule that I showed you in the beginning, that I told you I'm going to use in action. So what we are trying to compute is the rate of change of the angular momentum. So that's capital L is written as r, the position vector, crossed with m times v. So we are trying to calculate the rate of change of this cross product. And remember, we have this Leibniz rule telling us how to do this. Well, we have to do it one by one. First, calculating the rate of change of the first factor, then leaving the second factor untouched, and then adding to that the rate of the position vector crossed with the rate of change of m times v. Well, m is just a constant mass, it doesn't change. Okay, and this is what we are left with. Now let's look at what we have. We have r dot, the rate of change in position. Well, that's just the velocity vector, and we have its vector product with m times itself. Okay, and then what we have is the position vector crossed with m times the rate of change in the velocity vector, which is the acceleration, right? So what we have here, this first term has the vector product of a vector with itself, well, with a scalar multiple of itself. If you know about vector products, you know that this has to be the zero vector. Okay, so if you take a vector and take the vector product of that vector with a multiple of the vector, you get the zero vector. And what we have here is the position vector crossed with m times a, and that is the force, right? Newton's F equals ma is what we applied here. So what we have here is r cross f, and if f has the following form, if it's pointing in the origin, sort of the center with some magnitude. So this is the unit vector pointing towards pointing away from the origin, and this little fr would give us the strength, the magnitude of the force. Never mind that is just a scalar, that is just a number multiplying this position vector. And again, you see something that we have seen just a moment ago, a vector product where we have basically a vector and its scalar multiple multiplied, giving us zero again. So this is again the zero vector. Okay, so what we started from is the rate of change of the angular momentum, and what we ended up with was the zero vector. So what we see from this calculation is that the angular momentum is constant. Okay, so this is the conservation of angular momentum, and we did not assume that we have the inverse square law. We assumed a general central force, a general form for the force that was just pointing in the same direction towards the center, but we didn't say what the magnitude of this force was. Okay, now let's go to item pool again. So let me send you over to item pool once more, and let's try to answer the following question. So go to itempool.com /Kepler/live and answer this question. We have a rotating cloud of gas which shrinks to half its size. So imagine a cloud of gas which is rotating around some axis, and it shrinks to half its original size. The question is, how does its speed change? So what's going to happen to the speed of this rotating cloud? We have a few options. So the first option is that the speed doesn't change, it stays the same, constant. Or maybe the speed gets halved, so just like the size of the gas, it could be halved. Maybe the speed gets doubled, or the final possibility is that the speed gets quadrupled, that is four times as big. Okay, so I'm interested to see what you think. And I have a strong hint here in the form of an image, of a picture of a figure skater. So if you have ever seen figure skating, you should know what the answer is here, and it has to do. There's another hint. It has to do with the total angular momentum being conserved. Okay, so I'll give you another minute to think about this. What happens to the speed of this rotating cloud of gas as it shrinks to half its size? I'm interested to see what you think. Okay. So let me finish this poll and reveal the answer. I'm curious to see. So the correct answer was option C. Indeed, the speed gets doubled. Okay, so some people thought that it might get quadrupled, but in fact, if you want the angular momentum to stay conserved, remember the angular momentum was the vector product of r, the position, sort of the size of this cloud in this case, and its speed. So if the size shrinks to half its original magnitude, then the velocity has to double. Okay, so that's the idea. All right, so let's see, how are we doing now? Okay, now we can move on to the conservation of energy. Okay, so now we have seen that the angular momentum is conserved. Similarly, you can prove that in the case of our inverse square law, the total energy is also a quantity, a physical quantity that is conserved. Okay, so if you look at the total energy, it's 1/2 times m times v squared plus minus little k over r. Okay, here I have written a bit more general, written the energy in a bit more general form. So in fact, for any spherically symmetric force field, you will get your energy be conserved. And the way you can prove this is again a similar calculation. So here capital V is the potential energy, and the force is obtained from this potential energy by differentiating. So let me maybe quickly show you this derivation, but I guess I can already understand how it goes. Let me just make sure we really do. So what we have here is what we are trying to calculate here is the rate of change of the energy, right? So the energy is, of course, is written as 1/2 times m times v squared plus the potential energy, which depends only on the distance from the center. So that is why it's a spherically symmetric force field, because it only depends, the strength of the force only depends on your distance from the origin, and we want to calculate the rate of change of this quantity. Okay, so v squared, let me rewrite this slightly. So v squared, the length of the velocity vector squared, is the same thing as the velocity vector scalar multiplied by itself. So what I'm saying is that this is the scalar product of v with itself. So if you know your calculation with the dot products, you understand that taking the dot product of a vector with itself gives you the length squared. Now to this we add the potential energy, and we want to calculate the rate of change of this thing. So let's calculate the rate of change of the kinetic term. That is going to give us 1/2 times m times the rate of change of v dot v plus m times the v dot the rate of change of v. Okay, plus what we will get here is is the derivative of the potential energy, okay, multiplied by the unit position vector and the dot product of that with r dot. So this is something that's called the chain rule, what we applied here. The point is that what we are getting is, well, this is just the same two terms added up. So this is twice m times v dot times v multiplied by 1/2. So this is just m times v dot v. And then what we have here is this v prime, which is the force minus the force and the magnitude of the force times the unit vector pointing away from the center times well, dot product with r dot. Okay, so what we got here is nothing but m times v dot. So remember, v dot, the rate of change of the velocity vector is the acceleration vector. So m times a gives us f, the force, dot the velocity vector minus, well, what we have here is again the force vector times r dot, which is the velocity vector. So f dot v minus f dot v gives us 0 as a number, because we are taking the scalar product of f and v, right? So what we get here is 0, meaning that E, the energy, is constant. So the total energy of our system stays the same. Okay, so now we see that the conservation of energy holds true. In the Kepler problem, little f and capital V have these special forms. So the inverse square law and the gravitational potential that is inversely proportional to the distance. So what I want to show you next is another question in item pool. So let's head over to item pool. I'm curious to see if you can get this one right. So my next question is about objects that have zero total energy. Okay, so let's imagine that we have an asteroid heading in the direction, well, it kind of towards Earth, but it's going to miss Earth, so it's going to fly past Earth, but it has zero total energy. Okay, my question is, what is going to happen to this asteroid? Will it be pulled by Earth's gravity into orbit around Earth? Will it perhaps escape the gravitational pull of Earth and go off into space? Or will it maybe fall back onto Earth? Okay, so I have these three options for you. Will it be put on orbit around Earth? Will it escape Earth? Or will it fall back into Earth, basically killing everyone in the process? Hopefully not. So let's see. Go to itempool.com/Kepler/live and vote for your answer. Okay, so I already see 2 people have submitted their answers. So again, we have this object with zero total energy. So the kinetic energy is equal to the potential energy. And my question is, what's going to happen to this asteroid, this object? Will it be put into orbit? Will it escape the gravitational pull and go off to infinity? Or will it perhaps fall back into the center of the gravitational pull, which in this case, in this very scary scenario, might threaten us on Earth? So what do you think? I'll give you another minute and then I'll close this poll. Okay, I don't see any new submissions. So let me just finish. There is one. Let me just finish and reveal the answer. I'm interested to see if people got it right. So the correct answer was yes, option B. It's going to escape the gravitational pull of Earth and it's not going to fall back on us, which is good. So if something has zero total energy, it means that it has just enough kinetic energy to overcome the sort of potential energy that is required to escape from the pool, okay, and go off to infinity. Now, let me go to my notebook and show you quickly how this can be used to calculate the escape velocity that is required to escape from Earth. Earth is gravity, right? So if you want to put something in, not just into orbit, but to send it into to the moon, let's say, what kind of velocity, escape velocity you will need, can be calculated. So let me just quickly go to my notepad and show you how we get this calculation right. So here I have the total energy, that is 1/2 times the mass of my object times its speed squared minus what was it, g times m1 m2 over r. Okay, so if this is 0, I can express v using the masses and r. Okay, so v squared is going to be in this case is going to be in this case 2g times m1 times m2 over m times r. Well, remember m was this reduced mass, but in the case of a light object compared to Earth, which has a little mass compared to Earth, this is basically going to be the mass of that object, and we can simplify by that. So this is roughly true, meaning that the escape velocity is going to be roughly equal to the square root of this expression, which is 2 times the gravitational constant times the mass of Earth divided by the distance from the center of the planet. So that's the radius of Earth. So now I can show you this notebook again and this calculation for the escape velocity. So here we have the gravitational constant g, and the mass of the Earth in kilograms, the radius of Earth in meters, and here I have this expression that I have just written in my notebook. So this is the square root of 2 times the gravitational constant times the mass of the Earth divided by the radius of the Earth, and this is what we get, 11,186.4 meters per second. So it is roughly 11 kilometers each second, so more than 6 miles per second that you have to go and speed your rockets up to in order to escape from Earth. Okay, so if you look at the escape velocity for objects from Earth, you will see a number that is very close to being this figure. All right, so now we can use this little detour into the zero energy possibility to say something about planets, right? Because a planet is staying on its orbit around the sun. So in order to have a planet gravitationally bound into an orbit around the sun, it has to have a negative total energy. Okay, the energy stays conserved, but in order for it not to escape from the sun, just like our asteroid did from Earth, we have to have its energy, total energy, be negative. So capital E is going to be less than 0. But of course, this total energy is 1/2 times the mass times the velocity squared minus k over r. So what we have here in the first term, the kinetic term in the total energy is always non-negative. It's either 0 or positive, and it's most likely to be positive. But even if it's 0, if we sort of omit this first kinetic term, and we are left with only the potential energy term, we will get something that is less than the total energy, right? We are omitting a non-negative number, so we are getting something that is less than or equal to the original expression. So what we can say is that this negative total energy is greater than minus k over r, and you can rearrange this inequality to see that r is going to be strictly less than minus k over e. And remember, e is a negative number, so this is a positive quantity on the right hand side of this inequality. But what it tells us effectively is that r can never be larger than this fixed constant minus k over e, meaning that the planet will stay within a circle of radius minus k over e. So again, that's a positive number. Okay, so what we have seen here is that if we look at the sun in the origin and the planet moving around it, it will never escape from this circle of radius minus k over e. Okay, let's just connect the origin through the planet to a point on the circumference of the circle, on the perimeter of the circle, and this way we get a vector s. Let's also look at the speed, the velocity vector of our planet. That gives us a tangent line to the orbit of our planet. So this tangent line is called L. And what we can do with this point on the circumference of the circle, we can reflect it through the tangent line drawn to the orbit to get a new point. So this vector, I'm calling it little t. It's a vector that I got by reflecting this point on the circumference over through this line that is tangent to the orbit of my planet. Okay, and now a natural question to ask: what happens when the planet moves along its orbit? Well, of course, it's going to, let's say, go along the orbit this way, meaning that this point on the circumference is going to go around the circle. So you might think that when you reflect it over, reflect it through the tangent line, you might end up at a different place given by this vector t. But the point is that as the planet moves along its orbit, this tangent line will also rotate and sort of be more, well, horizontal in this case, leading to the reflection ending up in perhaps the same spot. So this is our geometric motivation to ask whether this point, this reflected point, will change in time or not. Okay, so this is our main question here. Does this reflected point change in time as the planet moves along its orbit? Okay, so let's try to express this vector little t using the quantities that we already know. Okay, so the total energy, the angular momentum, and things like that. So let's see if we can express this quantity. Well, if we want to go to this point given by the vector little t, what we have to do is go from the origin to r and all the way to s, and then we have to go down twice this distance because we are doing a reflection. We have the distance between the point s and the tangent line, and we have to go twice that distance in that direction to get to t, right? So what we are really doing is taking the vector little r, well, we take the vector s and subtract r from it, so to get this segment right here, and we want to basically project it over to this normal line, okay? Because that is parallel to this reflected line. Let me show you what I mean by that using my notepad. So here I have the same drawing, the same figure. So what we have here is this circle from which the planet can't escape, and then I want to have a vector that is perpendicular to the tangent line of the orbit, and such a vector could be the cross product of the linear momentum vector, that's just the mass times the velocity vector, and the angular momentum vector. Why? Because the linear momentum, the speed, the velocity vector times the mass points along the tangent line, so it's in this plane, and the angular momentum, remember, is perpendicular to the plane of the motion. So the angular momentum in this case is actually pointing right at you, perpendicular to your screen. So L is pointing right at you, and P is pointing along the tangent of the orbit. So if you take the vector product of these two vectors, you are going to end up with a vector that is again in the plane of the motion and pointing perpendicular to the tangent line. So that's our vector little n. Okay, let me write that down. So little n is P cross L. P again, let me just remind you, that's just the mass times the velocity vector. So that's the linear momentum, and L is the angular momentum of our body. And what we are trying to do here is we are trying to take this, find out what's the length of this segment. And for that, we are going to take this vector right here, which is S minus R, and we are going to project it down to this line, this perpendicular line. Okay, so let me go on to do that. So what I'm saying is, so let me just summarize what we know. We have this normal vector given by the vector product of the linear and the angular momentum, and then we have this vector pointing to the circumference of the circle, which has, the circle has radius minus k over e. Remember, e is negative, so this number right here is positive, multiplying the unit vector along r. Okay, so that's our vector s, and what we are trying to do is express this vector right here as a combination of the vectors that we already know. So what do we have to do? We have to take, in order to get t, we have to take the vector s, so go from the origin to all the way to this point along the circumference given by the vector s, and then go this way twice. So what is this vector from S to this tangent line? Well, this vector is S minus R. So this piece right here, S minus R, the dot product of S minus R with n, and appropriately sort of scaled. We have to divide n by its own length to make it a unit vector. Okay, so this is how you project a vector to a line. So this is the projection. We have to, of course, flip. So this is somewhere right there, some pointing in that direction. So we have to flip the sign and double its size. So this is how we get from the origin to t. Okay, so now we have this vector being expressed by using the things that we know. So let me go on and try to express this projection of S minus R to n, the scalar product. So can we maybe obtain a nice form for this scalar product? Well, both S and R point in the same direction. So they are parallel vectors. They are both a multiple of R, and I can write this as minus 1 over e. I can pull that minus 1 over e out and get e plus k over r times the vector r. Okay, so if you if you expand these parentheses, what you are going to get is minus 1 over e times k over r times r. So that's the vector s. And what you also get is minus 1 over e times r. So that's minus r. So that's just s minus r rewritten using the total energy. And n, remember, the dot product is taken with n, and n is nothing but this vector product of the linear and angular momenta. Okay, so this is the vector product of the linear and the angular momenta. That's the normal vector n. So now what we have here is a vector product of two vectors, and the position vector multiplied in a scalar product. Okay, so we have three vectors here. What we can do now, and it's a special property of the scalar and vector products, is that you can write the same thing, but the same sort of first term, and do the following. Take the first two vectors, take their vector product and the scalar product of that with the third vector. Okay, so you can basically change the two products. Okay, so this is something that these two products have in common. There is a nice geometric proof for this, but I'm not going to go into that. It has to do with sort of the geometric meaning of this triple product thing. So now what we have here is, you can recognize that right here what we have is the angular momentum. So that is capital L by definition, and it's getting multiplied to itself in this scalar product. So that will give us the length of L squared. Okay, so what we end up having here is minus 1 over e times e plus k over r times L squared. Okay, so this is what we got from the vector that we have to subtract twice of s after some rescaling. Okay, so let's see what that rescaling is. So that rescaling, that is n squared. Well, n squared is nothing but p squared times L squared. Okay, so we have this n given by the vector product of p and L. And since these vectors are perpendicular to one another, their vector product has a length that is the length of p times the length of L. So the length squared is the length of p squared times the length of L squared. But this can be slightly rewritten if we express p from the total energy. So for that, let me just quickly tell you that the total energy can also be written as p squared over 2m minus k over r. Okay, so that's the same thing. I have just rewritten the kinetic part using p instead of v, using the linear momentum instead of the velocity. Okay, if I do that, I can express p squared from this equation, and what I'm going to get is 2m times e plus k over r times L squared. Okay, so this is what I get for my normalization constant, this n squared that I have to divide by. So in the end, in summary, what we are getting here, if we put everything together, this vector t is going to be expressed as, you see, it's s minus twice this vector. Now we know what this vector is. We can put this all together and get 1 over E times m times the vector product of P and L, the linear and angular momenta, minus K times m over multiplied by r over its length. Okay, so this is what we get. Let me repeat that. So what we are getting here, so here is the same thing on the slides, what we have gone through. So in the end, we expressed this vector t using whatever we had before. So the energy, the linear and angular momenta, the reduced mass, and the position vector. So we expressed t by using these known things.